So let's make a stop and come back to the decision theory. So I suggest now to use decision matrices. Decision matrices are standard ways to represent simple decisions. So here we can represent our choices, for example, on the left, in case whether we would like to take this umbrella today or not to take the umbrella today. Of course, the outcome of our decision depends very much on the states of nature. If we take an umbrella and it doesn't rain today, we will have dry clothes but very heavy suitcase. If we not take an umbrella and it rains, of course we have soaked clothes and very light suitcase. So making these decision matrices, we can try to come up with a normative solution for the decision in this particular situation. So for example, we can assign numerical values to different outcomes. For example, we can like very much when we do not take an umbrella and it doesn't rain, and we do not like the situation when we don't take an umbrella and it rains. So we can assign numerical numbers for their utility of possible outcomes, and we can come up with a normative solution for this particular decision. So if we simply sum up outcomes for taking an umbrella and not taking an umbrella, we would see that perhaps expected value for taking an umbrella is higher than for not taking an umbrella. But the values or utilities of outcomes are not only aspects of our decision making that affect our decisions. So for example, if I offer you for free to select between two lottery tickets, in one lottery ticket you actually can win $28 million. In another lottery you can win $75 million. So which lottery ticket you would take for free? So perhaps most of you will take the second lottery ticket. But if I will tell you the number of tickets issued in this lottery, so in this case there is a chance to win lottery is 1 to 1 million, and for the second lottery the chance to win this lottery is 1 to 1 billion. So which lottery ticket you would take? If you simply multiply values by probabilities, you can see that actually expected value for the first lottery is highest for the second one. So a very rational person will actually select the first lottery. So this example illustrates that when we make a decision, we not just pay attention to the possible outcome in terms of the expected value, but also we integrate this value with the probability of this outcome. So this is an idea in economics called expected utility theory. So whenever we evaluate certain option, we integrate value and the probability of the outcome. For example, if there is a very small probability of raining, in this case, I just integrate the probability into the decision matrix. If you will calculate expected utility, you will find that with the low probability of rain today, it makes sense actually to not take an umbrella. If the probability of outcome is different, for example, if there is a 50 chance of raining today, it will change the matrix. So in this case, it makes sense from normative perspective to take an umbrella. So the idea is that during the decision-making process, we integrate probabilities of outcomes and the values of outcomes is called expected utility theory. This is a very influential normative economic theory, suggesting that we pay attention to the probabilities and the values of our outcomes. So this is a very influential theory. But of course, as we know from the number of behavioral economic studies, this theory doesn't explain our behavior, our decisions perfectly well. There are very serious deviations from the predictions of this theory. But this theory nicely captures that we integrate probabilities and values during the decision making. So how to investigate the process of integration of probabilities and values in our brains? We can use a paradigm suggested by Brian Knudsen. So here, at the beginning of the trial, subject can see a cue, and vertical line codes the magnitude of the expected reward. and horizontal line codes the probability of the expected reward. So here we can investigate how brain process expected probabilities and expected rewards. So how brain integrates these both aspects during the decision making. So subject has to press the button when the white square is presented on the screen, and in this case Q indicates that subject can actually get a very high reward with a very high probability. So as you see, at the end of this trial, the subject collected $5. So what Brian Knudsen found, that nucleus accumbens really code expected values. So activity of the ventral striatum of the nucleus accumbens is proportional, correlates with the expected values. As you see on the right slide, activity of nucleus accumbens perhaps not is ideally correlated with expected value, but still correlates with expected value in a certain way. So it looks like nucleus accumbens codes expected values during the decision-making process. We can actually investigate the same aspects of decision-making using a different paradigm. For example, in this case, participants play cards. And in one case on the left, participant can guess where the red card is located. So subject, in the first case, can open 4 cards, and in this case correctly predicted where the red card is located. On the right side of this slide, you see another condition, when subject can only open 1 card and guess where the red card is located. With this manipulation, we can actually manipulate the probability of outcome. In the first case, there is a higher probability to get positive outcomes than in the second place. We can also manipulate the amount of money subject expects to get during this game. So with this game, with this paradigm, we can make a look what is going on inside of the nucleus accumbens. So here you see that activity of nucleus accumbens is proportional to the expected magnitude of the reward. On the right side of the slide, you see that nucleus accumbens is particularly strongly activated when subject is expecting to get a higher reward. At the bottom of the slide, you see that also nucleus accumbens reacts to the probability of the outcome. So activity of the nucleus accumbens is particularly strong when subject expect to get rewards with highest probability. So actually, the same region encodes probabilities and values. If we will make a look to this map of the activity of the nucleus accumbens, you see that different regions coding probabilities and reward magnitudes are presented here by different colors. And these regions are overlapped a lot. So overall, it looks like nucleus accumbens is involved into the calculation of expected utility. It processes expected rewards. So it actually estimates the probability of the outcome, and it also estimates the amount of values related to the outcomes. So we can make some intermediate conclusions about the functional role of the nucleus accumbens. So first of all, as I suggested, from neuroeconomics perspective, our values are simply the firing rates of certain neuronal populations. So it looks like nucleus accumbens code anticipated gains magnitude during the decision making. It also looks like that certain neuronal populations of nucleus accumbens, they code expected magnitude of the reward, and some populations code probability of getting the reward. So it looks like this is a key region for the calculation of the expected utility during the decision-making process.